Assalamualaikum warahmatullahi wabarakatuh. Today we are going to present our robotic arm. We are from SCAM 2013 Mechanics of Materials. This is for assignment 2. Our lecturer is Dr. Ahmad Zahran bin Muhammad Kudzari, and our group members, the first is Muhammad Faris Akif bin Muhammad Fuzi, Nazmi Izzuddin bin Nazri, Unku Aiman Ashraf bin Unku Arifin, and lastly Syamil Khairuddin bin Muhammad Fauzi. So for the overview, we will discuss on certain key topics regarding our robot arm, which is the introduction, problem statement, objective, design process, material selection, manual equation analysis, and also simulation and results, and lastly, the conclusion. So two of the most important key points for robotic arm are, the first one is how it operates, and the second one is the material used. So this is the problem statement and objective. For the problem statement, the importance of strength testing for robotic arms. Robotic arms are used for precise operation in sectors such as manufacturing, healthcare, and automation. If the design lacks sufficient strength or isn't properly tested, it may deform, fail, or cause hazardous malfunction. Building physical prototypes can be expensive. Simulations offer a cost-effective alternative to validate design virtually before fabrication. And for objective, we need to assess how stress is distributed across robotic arm part using SolidWorks simulation, study the arm's deformation and displacement when subjected to applied forces, calculate the safety factor to confirm that the arm functions safely under expected condition, model realistic load scenarios including a fixed base and applied force at the end factor.
For material strength versus weight, selecting materials for robotic arms requires carefully balancing strength and weight to ensure optimal performance and efficiency. Material choice plays a crucial role in the functionality of robotic arms. Key considerations include tensile strength, overall weight, and cost effectiveness to create a design that is both reliable and practical for operation. Next, for significance of material selection, selecting the right material for a robotic arm is critical to its performance, efficiency, cost, and durability. The right material ensures the robot performs its task effectively in the intended environment while staying affordable and durable. We did researches for the suitable materials for industrial automation. For assembly, we use aluminum material for lightweight, corrosion resistant, and strong. And for carbon fiber, it is lighter than aluminum but a bit expensive. And for welding, we use steel alloys because it has high heat resistance and strong structural integrity under load. And next, for the drawings, engineering drawings, here are 3D view drawings and top view and the side view of the robotic arm. We use SolidWorks to fit these drawings. And next, for design details, we have properties for the assemble. For the mass, it has 299.371 grams, and for the volume, is 62.10697 cubic centimeters, and for the surface area, it has 489.80547 square centimeters.
For this robotic arm, we are using two materials. First, we are using a 1060 alloy of aluminum with a lightweight, a density of 2700 kg per meter cube, and with a yield strength 27.57 megapascal and tensile strength 69 megapascal. It is good for a component that requires a low weight and moderate strength. Second, we use a carbon steel sheet, which is it has a higher strength with a yield strength of 282.7 megapascal and also have a tensile strength 425 megapascal. It is suitable for parts that must withstand a higher stress. based on figure 5, we can identify where the force is applied on the robotic arm because from the figure 5, it is highlight the shaft joint where the stress will be concentrated. And on figure 6, it shows that the applied force at, at, at a single point rather than being evenly distributed. This result in concentrated node, which is critical for the stress analysis and could lead to localized failure if not designed properly. Because so you can see there are only one force, which is F on the shaft joint, and then for the manual calculation analysis from the figure 7, we know the mass of the upper robotic arm is approximately 0.2994 grams. To find the F or the force, we can use a gravitational formula for force, which is F equals to ma, with a gravitational acceleration of 9.8 meter per second squared. So when we use the formula, we can get the F, which is 2.9371. And then from the figure 8, it shows the length of the shaft where we can illustrate the free body diagram, and say we can see that um, the force applied on the shaft and then the length the shaft length A from the B, and then from figure 9 the shear force Dy can be calculated by applying the vertical force equilibrium Fy and the horizontal force equilibrium Fx. We know that sum of Fx and Fy will be equals to 0. And then we have to find the cross-sectional area of the cylinder by using a formula area equals to pi r square. We already know the radius of the cylinder, and then we can directly calculate the area. It's 2.0106 times 10 power of negative 4 meter squared. And then we have to calculate the shear force exerted on the surface by using formula tau or shear force equals to P over A. P is the shear force exerted and A is a cross-sectional area of the cylinder. Now we got the shear force is equals to 1.4608 times 10 to the 4 Pascal.
So here we are now for the computer simulation analysis. So this simulation shows a static stress analysis performed on a cylinder component using SolidWorks simulation. Okay, the model is subjected to series of downward force represented by the purple arrows applied on the top surface of the component. The green features on the sides indicate that the left and right face are fully constrained, preventing displacement in all directions. So the analysis type is focusing on von Mises stress distribution, which is commonly used to predict yielding of materials under complex loading. So the maximum von Mises stress recorded is approximately 6.20 megapascal, occurring the near top center of the Morse beam, where the force is most concentrated. The minimum stress is around 0.12 megapascal, found near at the center of the component. Here. The stress gradient is shown using a color legend ranging from blue, which is for low stress, to red, which is the high stress, indicating how stress distribute across the body. The video here shows the structure is well within the material strength of 620 megapascal, meaning it is safe under the given loading condition. Okay, as you can see, the von Mises stress is a scalar value used to predict the yielding of material under various three-dimensional loading conditions. It combines all normal and shear stress into one value. This is the formula for the stress von Mises. So the manual calculation, we got 1.4608 times 10 power of 4 Pascal. The simulation result is higher because it's considered the full 3D geometry of the part, including complex features like the curved shaft and account for the combined effect of multiple stress types. In contrast, the manual calculation is a simplified approach that typically includes only basic bending stress, leading to an underestimation of the actual stress experienced by the component. So, last but not least, for conclusion, analyze the shaft joint of a robotic arm using manual calculation and SolidWorks simulation. So, for the manual stress calculation, we got 1.4608 times 10 power of 4 Pascal versus simulated von Mises stress, which is 2.944 Pascal, showing the importance of the simulation tools. SolidWorks provide insight on deformation, fatigue, safety factors, and structural reliability. So they develop both technical skills, which is design, analysis, and simulation, and also soft skill, which is teamwork, communication, and task management. From this task, we gain valuable experience for the future work in mechatronic, robotic, and also automation. The project here highlighted the need to integrate theory with modern tools for safer and more efficient design. Okay, that's all from us. Thank you very much.